Hi, my name is Przemyslaw Delewski. It might be hard name for English speaker, but I'm generally from Poland. And the title for this talk is Transpiling, Go to Rust and Others. It's about others because the tool that I'll be talking about is can transpile Go code to other backend as well. And I would like to share with you some experiences working on this tool. Shortly about me, I am founding engineer at Quesma. We are working on reinforcement learning data sets for major vendors. Before that, I spent 15 years in observability space, mostly in Dynatrace and Sumo Logic, and I was also working on navigation software at TomTom. I am emeritus maintainer of PHP instrumentation, OpenTelemetry PHP instrumentation, and I am currently OpenTelemetry maintainer of Go compile time instrumentation. So, small disclaimer, this is the first time when I'm speaking about that project publicly, so I'm not sure if the flow will be perfect. And that's the agenda. So the background, what's the concept, what's the problem about, the problem that I want to solve, then the approach that I've taken in this project, which primitives are used, then I will tell you about compiler architecture and backend challenges that I had working on this project. And then, last but not least, I will be talking about optimizations. So, basically the background. What's the problem? So, at least a few times in my career, I had this problem where we had one component implemented in one language. It was, for instance, Java, and we wanted to have, the same implementation in C++, for instance. And there are many, at least a few ways that you can do that. You can solve this problem, but mostly, there are some problems with it. You can have some shared library that will be used across this language, across different languages. But there are problems always with algorithmic duplication, and when you fix bugs in one language, there are also bugs in other languages, and so on. So ideal, it would be to have one, implementation that will be deterministically transpiled to other targets. And as I said, there are a few existing solutions. One of them is FFI, so you can, for instance, have a code in C. You can expose the API in C and use it from other languages. But there are also other existing solutions, at least two that I know of, which are based on some idea of transpilation. And this is a HAXE programming language. And basically, that's just another language that you can use to write your, let's say, program. And then you can transpile this or compile to other backends. It supports many backends, like C++, PHP, Dlang, and so forth. The problem is that, for instance, with HAXE, if you would like to transpile to C++, for instance, it also comes with a runtime. So this runtimes, it links runtime, and this runtimes supports, for instance, garbage collection, because the language is garbage collected. But as we know, C++ engineers don't like garbage collection or any other this kind of penalty. And there is another solution that I know, which is very similar, is a fusion lang, and this is also it transpiles your code to other backends. It supports many programming languages, but also it do this work on a little differently because it doesn't link with, for instance, garbage collector, but they transpile. They have different types of pointers or references, and they are transpiled to different kinds of pointers. Like in C++, there is shared pointer, so they transpiled it into shared pointer, for instance, and use that kind of thing. But these two, solutions are just two new programming languages. And in Go any, I've taken different approach. At the beginning, of course, as I mentioned, I wanted to solve this problem of having just one implementation and transpile it to other languages. But I was thinking also about new language. But this is problematic for many reasons. So in Go any, I've taken a different approach. I just taken Go language and wanted to transpile it into other backends. This has, of course, there are many challenges. So the first question is which primitives we should support, and how can we do mapping to the other languages. And also there is a problem of memory model, because Go is garbage collected. Rust, C++ are mostly manual. There is manual memory management. Java and C# and JavaScript, they are similar to Go because they are also garbage collected languages, but they are mostly reference-based, and Go is value-based, so it's always copy. It's always about copy value. And now, if we look at the trade-offs between having a new language and just do a transpilation from existing language, is of course you have syntax freedom. For instance, you can choose whatever syntax you want. Then for the tooling, you have to build everything from scratch. And when you support existing language, you have already these tools, so you can use them for free. Of course, there is a learning curve. You have to, learn the new language, totally new language. And if you're using existing language, you know this, and you can use your existing knowledge. Then the ecosystem exists, and basically that's it. So generally, I started with very limited subset of Go, and transpiled it. I built all the backends, transpiled it this minimal subset to all the backends, and basically the goal is the main idea behind this is that Go any is a valid Go program, but not vice versa. So any Go any program is valid Go program, but not vice versa. And now core primitives. So as you know, every language has to support types, then variables. So we have to basically support expressions like arithmetic expressions, logical expressions, and then there is a control flow. So we have to support this kind of statements like if, else, switch, and for. So that's basically loops, and basically functions. And that is true also if we look at the assembly language. So only minimal set of these primitives are needed to express the whole program. And everything what we have above that is a kind of syntax sugar. So mostly this is about our convenience, or sometimes to do the performance. So there are new instructions added for the performance reason. For instance, to the assembly, so new processor instructions. But basically, we need only few primitives to write programs. Now, I also taken one key decision about not supporting pointers and references, because not all backends supports may have support for references or pointers, and that might seem as limitation, but I will show you that then I can transpile the pointers to this limited subset and do other transformations based on this limited subset. So first demo I wanted to show you. So I wrote a limited version of Commodore 64 emulator. This is not full emulator because it's a hybrid code. So basically, keyboard handling is just a normal Go code. So that's just normal Go code. And also for video controller, this is just a normal Go code. But any other things like a full instruction set of MOS 6502 processor is implemented here. There is basic support for this. There is basic programming language implemented. I think 99% of that I implemented here. So for instance, that's a very basic program. That's I think, first program that I ever written. And we can run it here, and that's what I'm showing you is basically, so this is the Go code, so this is implemented in normal Go, but it's transpiled into JavaScript, and that's why you see it that it is run now in a web browser. So in order to just transpile that, I have to use this kind of command, and I can do that now and compile that to Rust to show you that it works also, with other backends. I can do that from one code. There is a lot of these warnings reported, but this is mostly about identifier, because Rust supports this snake case and not the camel case that normally Go is using. I could also, transform that identifiers to the way that Rust needs, but this is something that is not very important. So that's the same version of this code compiled to the Rust. And now every language also needs some kind of runtime support. So there is usually some kind of runtime library that this is mostly some kind of intrinsic. So usually there is some C API that is exposed, and you can use this from other languages. Basically, you need that for some I/O. So this slide shows that this GoAny comes also with I/O support for reading files, for network operations, and some other things. And that's how we link that with your program. So when you have an import for runtime FS, for instance, this is file system library, and then you use it for reading files or any other operations, then it will just generate some additional artifacts. If you, for instance, transpile it into C++, there will be a makefile generated and some additional stuff in the makefile to build it then fully. And one of the demo that I would like to show you regarding this runtime support is GUI, some small GUI library. This is also implemented in Go and then transpiled into JavaScript in this case. So as you can see, there is a few widgets. So I have a runtime library for GUI. It's exposed only the basic primitives, and then there is also library built on top of this runtime that is used for widget implementation. So there are several widgets implemented there. Now the compiler architecture. So as I said, I started with a very limited set of primitives to only have this support for expressions, some if-for loops, switch, slices, and structs and functions. And over time, you can, of course, build programs in this way, but it might not be very convenient. So then I started thinking about supporting other features that Go has. So, for instance, pointers, interfaces, methods, closures, variadics, differ, and so on and so forth. And so basically, the compiler has several passes. As you can see on these slides, there is a syntax check first. There is a semantic check, semantic pass that in fact it is invoked for several times. There is lang sema lowering, then further method lowering, interface lowering, and again sema we are checking if everything works correctly or if we don't have any bug or any problem. Then there is a pointer lowering and some kind of memory layout pass which is doing optimizations. And then on this, finally on this, after these transformations, we have backend emission. Now I will go deeply what the specific passes are doing. So first was lang sema lowering. So basically, this pass is transforming the code into some, it is doing some normalization. So basically it might be that some constructs are not available in backend language. So I'm doing some transformation to have a common delimiter, representation. And so for instance, name returns. This is not something supported in all languages. IOTA expansion, variadics. I'm also transforming make call because I could do that support in each backend, but I made it simpler, and there is only one make supported by all backends. Integer range also is converted to classic for loop, type switch, the same, and the other constructs like a differ, multi-assign, also shadow the vars. This is something needed for C#, because in C# you cannot shadow variables. There will be error return. Field constructs, if you have the same field name as a type, then C++ also emit an error, so it is converted into some other name. Now method receiver lowering, so This limited set doesn't support normally methods, so I'm doing some kind of transformation, and the method receiver parameter that you can see here is just transformed as and added as a first parameter into the normal call. Then interface lowering, so interface before is transformed into something like you can see here. So there is data field added as an interface type, and there is a function. This is a kind of callback dispatch method. Then it will be, this is what you will see in the assignment side. So this kind of variable will be created, writer in this case, and then write function, callback function, or method dispatching will call this normal, ordinary file write function with passing this data, this file parameter. And pointer lowering. So basically, because we normally don't support pointers, but what we are doing, we are converting them into some kind of pools. So we have a pool, and pointer is just an index into this pool. So basically, that's how it works. This also opens some opportunities regarding performance optimizations. And now this is in detail how this pointer lowering works. So for instance, here main is a caller. So in this caller, when you have function like in the second line, there is a new particle function. And this function normally will be, one of the parameters will be just a pointer to this particle. So then we just pass pull particle to this function, and this pull particle is also returned back with an index that was assigned to this pointer there. So basically that's how it works under the hood. Now the backend challenges that I had, there are different, as I mentioned, there is, for instance, in C# there is variable shadowing. So we have to transform that into something that do not produce an error. And for Java only supports signed types, so no unsigned types. So we have to do all the transformation based on signed types only. There are also some challenges with lambdas and function interfaces. Now in C++, we don't have a string switch, so we have to lower that to the if-else statements. Field name collision, this is something that I mentioned before. Multi-assignment, this is also not supported in C++, so we have to transform that into normal one-to-one assignment. And in Rust, we have move semantics by default. So the transpiler is generally very conservative. It always adds clone whenever there is something passed to the function, the type that is not copyable normally. And there is also challenges with borrow checker. So there are many cases that we need to support in order to work that correctly. And no implicit numeric conversions. So this is something that we have to also find and transform in some way. In JavaScript, there is no block identifiers, no integer types, and no struct types. Now, optimizations. of course, there are different challenges, but mostly the most interesting ones are in C++ and Rust. And as I mentioned before, first pass normally adds a clone every time when there is a value passed which is not copyable normally. And so we are adding call, but this clone means that we generate a lot of overhead, and that's one of there are several patterns that we have to handle, and as you can see here, that's how this transpilation is done. So we have a Go code here, and this is an example of the code, and then we are transforming that into something like that. So we are adding these clones, but in this example of emulator, C64 emulator that I was showing you, this was generating about 300 megabytes unnecessary mem copy. So and it was extremely slow, and I will show you later, a little bit later, how slow it was, showing a different demo. So basically, regarding optimization, there are three-stage optimization pipeline. So first, emitter generates these clones, but then we are removing, or we are changing these clones whenever it's possible to move. So we are trying to move variables. And then also there is a reft optpass, which is basically about not cloning, but just passing by reference whenever also there are some rules that we can prove. And there are two switches generally used for optimization currently in this transpiler. Optimize moves. So as I mentioned, we are trying to just move when you have this code like here. So we are passing some value, and then we are returning it back. It means that we can just move it. So normally the clone is generated, but we are optimizing that just using move here. And there are, as I mentioned, there are some rules. So variables has to appear on left hand of assignment only once on call arguments and not inside the closure. And there are also additional patterns that GoAny is distinguishing or can handle. So basically, here is about extracting some temporary variables, and then if we have two arguments here, so we cannot, of course, move the first argument because there is also a field of this struct, for instance, and we have to first extract temporary, and then we can just move two variables there. The same thing if you would like to reduce this clone here in this kind of thing. So there is a state struct which has additional or which has field inside it called C, and in order to just remove this clone, we have to use memtake, which internally just moves this state C field. It is implemented in Rust. This is just a function in Rust in std memory, and internally it uses unsafe mode to implement that move. And there are other examples of patterns that generally this GoAny can handle. The same situation we have for C++. We are trying to use std move whenever possible. And we are trying to eliminate also clones in this standard library calls. For instance, len, it's very often time use function. So there are many calls for clone whenever we used len call. So that's important case to optimize as well. And so on and so forth. And as I said, there is also optimized refs, which is about just using, just passing argument by reference. And in this way, this example that I was showing before, emulator, we reduced a number of clones to 484. So it's about 500 clones, calls down to 16.1 only. Yeah, and I wanted to show you to build this another demo to show you how slow it is generally without this kind of optimizations. Okay. Maybe I will do it this way. This is just another example, text scroll. So I will build it, and I will now run it. Probably I haven't changed the name of the generated binary, but that's the effect. So it's extremely slow, as you can see here. And now I will try to compile the same code with these optimizations. Okay. So now it's much faster. So after elimination of all these unnecessary calls. And so there is one other optimization that I would like to show you. I'm not sure if we have time, but there is also another switch that recently I added to this transpiler, which is about optimizing memory layout. And whenever it's possible, the GoAny tries to, to find specific constructs and some patterns, and whenever that's possible, it can, transform this kind of when we have arrays of something, it can change this to SO architecture. So there will be structs of arrays then, and just to show you the result that we have at the end. So normally, when you compile that in normal Go, we have about three seconds. This how much time it will take to execute this demo program, and then after all the optimizations and transpiling into the C++, which is the most performant one, is less than 1 second. But I didn't mention that there is also a Go backend, so I can just transpile from Go to Go. And when I also, compile it with these optimizations, so it will, from 3 seconds, we will have about 2 seconds. So it is faster than the normal Go compiler. In this case, of course. So, and yeah, so I can show you that. However, not sure if we have time for that. So basically, this project is ongoing research. So basically, I'm interested in few areas. Here, the intermediate representation design, compiler architecture, memory model, and optimizations. And of course, there are some limitations currently because the Go ANI doesn't support standard library, for instance. So you cannot just take normal program and recompile it, because we don't have the support yet. But what you can do, you can just write your own programs, and then it has to be self-contained. So it has to have all the things that are needed, all the dependencies. And you can be based only on the runtime supported by Go ANI and libraries that are already there. So basically, that's the limitations, current limitations. Yeah, and the next step probably would be to add support for this standard library and to check how far I can go with it. So basically, that's it from my side.